We also now know that Saturn is orbited by over 60 natural satellites. The largest of Saturn's satellites is a moon called Titan. It is enveloped in a thick atmosphere, one filled with orange haze. In 2005, a NASA probe penetrated the veil of mystery and sent back the first images of the surface. The terrain looked amazingly familiar. Black lines branched out over the surface. They looked just like rivers. And numerous lakes were discovered. This was the first time any celestial object had been found with liquid on its surface. The more the probe investigated, the more Earth-like Titan seemed to be. It was at this point that scientists began to suspect that life might be present.
Maybe in the seas, more interesting things happen. Maybe you get self-replicating chemical systems, much like those that are the first steps towards living systems that were deep in our own history. So Titan gives us a whole new set of possibilities.
There's the possibility that maybe there is life on Titan that has somehow found a way to make use of all of these building blocks that the atmosphere is making for it.
However, the temperature on Titan is minus 180 degrees Celsius. Could life really exist there?
Well, how do we know it's too cold? Imagine you're living on Titan and you're looking at the Earth. You'd say, oh, there's a liquid, there's organics, there's energy, but it's too hot.
Titan has both an atmosphere and liquids. Could life exist there? This planetary body, very similar to Earth. Saturn's moon, Titan. Imagine the journey from Earth to Titan. If you could travel at the speed of light, you'd pass Mars about 4 minutes into the voyage. At the 30-minute mark or so, you would pass the giant ball of gases known as Jupiter. Then, some 70 minutes after departure, you would finally arrive at Saturn, surrounded by those beautiful rings. Like Jupiter, Saturn is a large, gaseous planet. Finally, you'd reach Titan. With a diameter of 5,000 kilometers, Titan is about 3/4 the size of Mars. It's a moon the size of a planet. Fully cloaked in that orange haze, Titan's true appearance was not known until the 21st century. (1997) saw the launch of the Cassini-Huygens mission. The Cassini orbiter, equipped with cameras and other instruments, and carrying the Huygens probe, was sent to investigate Saturn and its moons, especially Titan. In 2004, 7 years after liftoff, Cassini-Huygens reached the vicinity of Saturn, 1.4 billion kilometers from the Sun. Cassini then proceeded to enter into orbit around the planet and its satellites, and to commence scientific observations. It took this image of Titan. For the first time, Titan's true features began to show from under that thick haze. The day was approaching when we would finally be able to see the surface of Saturn's giant moon. In December 2004, the Huygens probe separated from Cassini and coasted to Titan. The target landing site was near Titan's equator. What that site would be like, no one knew. Titan's atmosphere is 1,000 kilometers thick. The probe entered it. Huygens deployed a parachute and drifted down, jettisoning its heat shield. This image, taken from a height of 152 kilometers, was Huygens' first view of Titan, which was still obstructed by haze. Huygens was shooting still images as it descended. Its microphone also captured the sound of the wind rushing by. This was the first sound recording ever made of an alien environment. These images of Titan's surface were taken by Huygens from 16,000 kilometers up. Black veins, like the branchings of a river, are visible. It does look as though they are flowing to the mouth of a river. Now, from 8,000 meters above Titan, it looks just like the sort of coastline we're used to seeing on Earth. Finally, the landing. This is an image taken by Huygens just after landing. What look like rocks and pebbles strewn about over a flat plain are actually chunks of ice. The surface temperature is minus 180 degrees Celsius. Atmospheric pressure is a little higher than Earth's, 1.5 bars. The horizon seems blurred by mist. This is exactly like some rocky desert landscape on Earth. High above, the Cassini orbiter continued its observations. In the equatorial region where the Huygens probe landed, Cassini discovered a strange pattern. Some sort of regular striping. Further observations found similar striations covering some 20% of Titan's surface. Ralph Lorenz has dedicated himself to investigating this strange striped pattern. He is trying to solve the mystery of Titan's stripes by comparing them to patterns he finds on Earth. This is the Mojave Desert in the western United States. Lorenz believes Titan's stripes are like the peaks and troughs of desert sand dunes. There are indeed real similarities.
It's remarkable somehow that despite the different gravity, the thicker atmosphere, and the different material that the sand is made of, somehow the landscape ends up looking almost exactly the same as many places on Earth. By comparing the shape of the dune and the interaction with the rest of the environment, we can get an understanding of how these structures formed. And for example, different shapes of dunes form in different wind patterns.
So the goal is to solve the mystery of Titan's stripes by investigating terrestrial desert dunes. Lorenz's first step is to send up a kite with a camera for an aerial overview. He's looking for a place that has a striped pattern like Titan's. Next, he mounts a dune buggy equipped with GPS. He wants to measure the heights of dunes and the angles of their slopes. The shapes of sand dunes change by the minute. Lorenz plants a stake with a streamer attached. In fact, he plants a whole line of them along this slope. This will show what sort of wind creates this type of dune. The wind is blowing from screen left, across a gentle slope. Then it swirls around, as if to carve out that slope to the right. So it's become clear that here the wind flows from the milder slope over and down the sharper slope. Lorenz believes that the stripes on Titan are also wind-sculpted sand dunes. A closer look at that image of Titan's stripes shows ridges with milder and sharper slopes, similar to those in the Mojave Desert. So Lorenz conjectures that the wind on Titan must have been blowing from left to right. The winds blowing on Titan's dunes, however, are thought to be weaker than the winds on Earth. The reason for that is that Titan's gravitational force is only 1/7 of Earth's. A relatively small action can produce a big result. So on Titan, effects similar to those seen on Earth are being produced by mild winds.
Titan is still an active world where, geologically speaking, processes are still happening. And the fact that we can see sand dunes, for example, suggests that the winds that move the sand around are still active, that we're seeing a dynamic planet, much like the Earth.
There was another unexpected aspect to those images taken by Huygens. Look closely at those chunks of ice on the ground. They are reminiscent of stones turned over and over by rivers on Earth. Sharp edges are worn down. They're rounded, like pebbles. So there may well be liquid on Titan. This discovery attracted attention and astonishment. Meanwhile, the Cassini orbiter made a surprising discovery of its own. Black spots and blotches were visible near Titan's north pole. Radar observations showed them to be lakes, filled with some liquid. They number in the hundreds, and some of them are huge. This is the first time liquid has been found on the surface of any celestial body other than Earth. The lakes are dotted with islands and fed by rivers. But with a surface temperature of minus 180 degrees, any water on Titan would have frozen. What liquid could it be in these lakes and rivers? This is it. Liquid methane. On Earth, it's normally a vapor, but at extremely low temperatures, it condenses into a liquid. Methane melts at minus 182 degrees Celsius. It boils at minus 161 degrees. In the 20-degree range between those two extremes, it exists in a liquid state. The temperatures on Titan's surface are just right for liquid methane. Methane is composed of one carbon atom and 4 hydrogen atoms. It's the simplest hydrocarbon, and it constitutes the bulk of the liquid in Titan's lakes. A portion of the liquid is ethane, another hydrocarbon with similar characteristics. Scientists at the Jet Propulsion Laboratory are trying to determine how Titan's methane lakes were created by conducting experiments here on Earth. Christophe Sautan is an expert on bodies of ice found in the solar system. This device is called the Titan chamber. With internal air pressure at 1.5 bars and a temperature of minus 180 degrees Celsius, it reproduces Titan's environmental conditions. Inside is placed a disk of ice, standing in for the terrain on Titan. They then release droplets of liquid methane onto the surface of the ice. The methane disappears immediately, absorbed by the ice, like water being swallowed up by a thirsty earth.
So the big surprise, something we did not expect, is that when the methane falls on the ice, well, actually the methane got sucked into the ice. It gets absorbed. It doesn't run on the ice.
However, if methane continues to drip onto the ice, eventually it begins to pool on the surface. This suggests that wherever there are lakes on Titan, the surrounding ice must be saturated with methane. During its landing on Titan, Huygens measured the concentration of methane. That concentration gradually rose the closer the probe got to the surface. Then, the moment it landed, there was a sharp increase. It is thought that this was due to the heat from Huygens vaporizing the methane that permeates the ice. On Titan, liquid methane acts in ways similar to water on Earth. In June 2012, for example, Cassini observed a strange phenomenon near Titan's south pole. An oddly shaped mass seemed to be squirming about in the atmosphere. It was a cloud, swirling. A cloud made up of methane. On Earth, water is recycled as water vapor and rain. One of the factors prompting this is seasonal change. On Titan, the same sort of mechanism seems to be at work. Titan is tilted on its axis, some 26 degrees off vertical. The Earth has a 23.4 degree tilt. It's another point of similarity. Along with its parent planet, Saturn, not shown here, Titan takes 30 Earth years to orbit the Sun. The tilt of its axis gives birth to different seasons. At this location, Titan's northern hemisphere experiences the long days of summer. The northern hemisphere is warmed, producing rising atmospheric currents. Liquid methane on Titan's surface evaporates and is carried southward. Near the South Pole, it is winter. The methane gas is cooled, condensing into a liquid or even solid state. It can form clouds. Like that huge swirling cloud Cassini spotted. When it's winter in the northern hemisphere, the cycle reverses. Now the methane cloud forms near the North Pole. Underneath that cloud, methane rain begins to fall. Since methane is more viscous than water, its raindrops are larger, with diameters of about a centimeter. But as Titan's gravity is weaker than Earth's, the droplets fall more slowly, about 1 meter per second, like a soft snow on Earth. They soak the icy ground on Titan and form lakes. Wind blows, rain falls. When people could finally see Titan close up, they were astonished at how much it resembles Earth. In 2007, the Cassini orbiter spotted something truly peculiar on Titan's surface. A land formation, some 70 kilometers across, in the shape of a flower. What could it be? Perspective can be gained by combining images taken from two different points of view. A three-dimensional image of the topography emerges. That strange formation turns out to be a rugged mountain, featuring a 1,500-meter high peak. There's also a chasm that looks like it might be a volcanic crater. From that, one can infer a formerly active volcano. That volcano has been an object of particular interest to Jonathan Lunine, an expert on Titan's internal structure. He says that the volcano did not spew lava. Rather, it pumped up a mixture of ammonia and water.
One thing to remember is that when water is mixed with ammonia, it can stay liquid down to very low temperatures, down in fact to minus 100 Celsius. But at that point, within a few degrees of that point, the liquid is actually very viscous. It's almost like basalt. And so if that is what is flowing out on the surface, we would see very thick flows.
Lunine believes that under the ice beneath the volcano, there's an ocean. He came to this conclusion due to changes in Titan's shape. Titan completes its elliptical orbit around Saturn once every 16 days. During that time, it regularly feels the changing effect of Saturn's gravity. In short, it experiences tidal forces. At its farthest point from Saturn, Titan is almost perfectly spherical. But at its closest point, where Saturn's gravitational pull is the strongest, Titan grows fatter. Its diameter alters by as much as 10 meters. Lunine says that Titan can transform so dramatically because internally it is not made entirely of solid rock. Lunine's observations suggest the following picture of Titan's structure. The outer crust of ice is some 50 to 100 kilometers thick. The center is comprised of two types of bedrock. In between the ice and the rock, however, is a layer of liquid water. The bedrock generates heat, says Lenin, permitting the water to remain in a liquid state. This ocean layer is some 300 kilometers deep. Ammonia, present in Titan since its origin, has also dissolved into the water. It is thanks to this ocean layer that Titan can change shape so flexibly.
The interior is warm enough that really only liquid water is a suitable, stable material in that region. So we're pretty sure from the gravity experiment that Titan has a liquid water layer under its surface.
According to Lenin, the tidal forces caused by Saturn in turn stimulate volcanic activity. Tidal forces cause friction along the boundary between the ice and the subsurface ocean. The water heated in this way melts some of the icy crust. It builds up like terrestrial magma and eventually forces its way up above the surface. This ammonia-laden water flows out from Titan's volcanoes like lava. Lenin believes such volcanoes are proof of an underground ocean. Beneath Titan's icy shell, a whole new world lies hidden. Saturn has over 60 moons. Among them are Enceladus, ice-covered like Titan, and Hyperion, pockmarked with craters. Mimas has this huge crater. Those are just a few of Saturn's moons, but they all have practically no atmosphere. Only Titan boasts an atmosphere that extends as far as 1,000 kilometers into space. Actual measurements reveal that this atmosphere is 98% nitrogen. The rest is largely methane. Why is Titan the only one of Saturn's moons with a thick atmosphere? Solving that mystery through experimentation on Earth has been a preoccupation of Yasuhito Sekine. Sekine believes that Titan's atmosphere was generated by an extraordinary mechanism. The mechanism? Collisions with small celestial objects. Sekine is trying to reproduce that effect using a laser. When Titan was first formed, its icy landmass contained about 1% ammonia. So inside a vacuum chamber, a disk of ammonia water ice stands in for the young Titan. The laser beam enters from the left of your screen. It strikes a projectile, which then impacts the ammonia disk. That was the laser shot. Gases released by the impact are measured. One is nitrogen, released by the disintegration of the ammonia. Titan's thick atmosphere contains large amounts of nitrogen. According to Sekine's calculations, based on his experiments, repeated impacts by small celestial objects could have produced just such an atmosphere.
タイタンの地殻中にもともと入っているぐらいのアンモニアの量があれば今の 1.5 気圧の窒素の大気を作ることができるということを明らかにしました。 重要な点はですね、大きい天体でないと大気を重力的に持てないということです。なので他の衛星たちは同じように衝突は起きたんですけど、それぞれが小さいがために窒素の大気を持つことができなかったと。
For example, Enceladus, one of Saturn's other moons, is merely 500 kilometers across. That is 1/10 of Titan's diameter. Saturn's other satellites are also small, with weak gravitational fields. So even if they've been similarly impacted, they haven't been able to hold on to any atmosphere. But did Titan in fact experience repeated bombardment by small celestial objects? Hal Levison uses computers to calculate the history of the solar system. He has advanced the revolutionary theory that some 4 billion years ago, the entire solar system was shaken by a massive event. Levison argues that when the solar system was forming 4.6 billion years ago, Uranus and Neptune were closer to the Sun than they are now. He inputs the location and size of the planets, and also of the small celestial objects that lie further out. Then the simulation begins. At first, the basic situation did not change much. But some 600 million years later, Uranus and Neptune were suddenly flung to the outer realms of the solar system.
Then out, okay? And that caused the giant planets to slowly spread. It was infinitesimal. You wouldn't have noticed it, but the orbits were slowly changing. And that continued until Jupiter and Saturn got to the point where Jupiter was going around the Sun exactly twice. Every time Saturn went around once, and that configuration is what set the whole instability off. Okay, so you went almost overnight from a time when, okay, there was a little bit going on, but not much, to this very violent period where all hell breaks loose.
The smaller celestial objects, shown here in green, had formed a ring at the outer edge of the solar system. But then the gravitational force of Uranus and Neptune violently scattered these objects. The result was that in the period from 4 billion to 3.9 billion years ago, the planets of the solar system encountered a barrage of small celestial objects. During this period, Titan also was hit repeatedly, developing a nitrogen-rich atmosphere. That made it a very special moon.
たった1億年とかそれぐらいの短い期間なんですけど、その間にですね、その 1.5 気圧という膨大な量の大気を作ることができたというふうに考えられます。タイタンっていうのはですね、唯一人類が初めて見つけた生きている天体だというふうに言えると思います。で、地球と同じようにですね、表面で液体が存在して、それが蒸発して雲を作って雨を降らしてというような循環が起きているのはですね、現在の太陽系の中では地球とタイタンだけです。で、その点において40億年前のその出来事というのはタイタンにまさに命を吹き込んだと、生きている天体にしたという意味で非常に画期的な出来事であったというふうに思っています。
1977 saw the launch of Voyager 1. Its mission? To explore and observe the outer planets, from Jupiter to Neptune. This was its view of Titan. It was a close look, but still the moon was shrouded in a thick orange haze. However, even then, one scientist maintained that the haze held the secret to sparking life below. Bishun Kare has been trying to penetrate the mystery of Titan's haze since the early 1970s. He participated in the Voyager mission. He has focused on the haze as being itself a source of life. Carré introduces a nitrogen-methane mix into a sealed flask to simulate Titan's atmosphere. The flask is fitted with electrodes. Now Carré discharges them. This is meant to reproduce the effect of lightning or other energy surges on Titan's atmosphere. It's about 10 hours since the start of the experiment. A reddish-brown substance has become visible inside the flask. Carré claims that this is the very same substance as the haze enveloping Titan. So what happened inside that glass vessel? First off, the electrical surges split apart the molecules of nitrogen and the methane. Their atoms recombine with carbon and other atoms in all sorts of ways, forming a variety of new organic compounds. Analysis showed that some 200 types of organic compounds had been created in this experiment. Organic compounds are the materials out of which our own bodies are made. They are the building blocks of life. It was thanks to Carré's work that Titan came to be considered one of the celestial objects on which life might exist. The Cassini orbiter's close-up observations of Titan have come some 30 years after Carré's experiments. Will they confirm that Titan's hazy atmosphere has in fact given rise to organics? The INMS is a device that measures molecular mass. Cassini has used it to determine the composition of Titan's atmosphere. Cassini's data were streamed back to Earth, where they were analyzed by Hunter Waite and his colleagues. Waite led the team that designed the INMS instrument package carried aboard Cassini. Waite's lab was able to reproduce and confirm Cassini's data by utilizing the same INMS system. They could then analyze accurately whatever molecules or compounds the instrument had detected. The results were astonishing. Rendered in the form of a chart, each of the different molecules identified by Cassini is represented by its own colored area. Various organic substances were created in Titan's atmosphere, ranging from ones with a single carbon atom to more complex ones with 6 or 7 carbon atoms.
When Cassini sent back data, we found out that the upper atmosphere was much more relevant than we ever thought, that most of the chemistry seemed to be going on in the upper atmosphere, that very large molecules were being created in the upper atmosphere, way beyond our expectations. Titan is one of the best organic factories in the solar system.
Bathed in ultraviolet and cosmic rays, Titan's upper atmosphere is continually engaged in converting nitrogen and methane into a rich array of organic compounds. As these compounds collect in the lower atmosphere, they produce Titan's famous orange haze. Finally, they are precipitated, with methane rain, onto the surface as well. It's been 4 billion years since Titan's atmosphere was formed. During that time, it is estimated the organics settling onto the surface have created a layer dozens of meters thick. The dunes discovered near Titan's equator are thought to be a large deposit of these organics.
Now on Titan, the sand is made, we think, from organic material, and we think that material comes down and gets built up into sand-sized particles that are then accumulated by the wind to form dunes much like these.
Amidst this accumulation of organics on Titan's surface are substances of vital importance to the emergence of life. That finding was made by a young researcher with a specialty in organic chemistry, Sarah Hurst. Hurst has undertaken a minute examination of the organic compounds discovered in Titan's atmosphere. She's written her own computer program to do that. Based on Cassini's observational data, she faithfully simulates the composition of Titan's atmosphere and produces the same organics. Next, she uses her computer program to determine the molecular structure of every compound.
These peaks right here are the masses of the ions in the mass spectrum data, and then it's the number of carbon, nitrogen, oxygen, and hydrogen in each of those peaks. And so then what the code does is it goes through and compares this information to a list that I've given it of all of the amino acids and nucleobases that we're looking at. So here we have, at 136, we have the molecular formula of adenine, which is 5 carbons, that matches. It has 5 nitrogens, it matches. No oxygen, and then 5 hydrogens. So we know from this that we have the molecular formula of adenine in this sample.
Genetic information for all life on Earth is encoded in DNA. Adenine is one of its 4 major components, or nucleobases, and all 4 have been produced in Hurst's experiments. If these nucleobases combine in such a way that they create DNA, then a huge step forward will have been taken towards life itself. With this discovery, speculation mounted that Titan might actually be capable of harboring life. Life on Titan? It may in fact already exist. If it does, what would it look like? The search is on for the answer. Trinidad and Tobago form an island country in the southern Caribbean. They have a population of about 1.3 million. They also have one of the most unusual lakes in the world. It's called Pitch Lake. It contains not water, but naturally occurring asphalt. It bubbles up from an oil field that lies underneath, creating a lake of asphalt that's 40 hectares in area and 80 meters deep. Strangely enough, Pitch Lake is the site of fieldwork being done by astrobiologist Dirk Schultz-McCook. He thinks that Titan is the best candidate for the location of extraterrestrial life. He's come here to try to envision what life forms on Titan might be like. Asphalt, like methane, is a hydrocarbon comprised entirely of carbon and hydrogen. You wouldn't think this was a substance that harbors life, but Schultz-McCook says it actually does contain microorganisms.
Well, this is one of the few environments where it's similar to Saturn's moon Titan, where we know that we have hydrocarbon lakes on the surface. Obviously, Titan is very cold, so it's still different than from over here. But we do have the liquid methane and ethane, which are also hydrocarbons. And if we can find out what kind of organisms are living here in the asphalt lake and how they adapt to living in the hydrocarbons, we think we can get some ideas to how life could operate on a moon like Titan.
Asphalt contains almost no water.
Did you say that there's microbes in it?
Yes, there's microbial organisms in that liquid asphalt.
In this thing?
In this thing, yeah.
Like maybe 1, 2?
Millions.
Millions?
Yeah.
Genetic analysis identified some 600 new types of microorganisms living in the asphalt. Most are archaebacteria, related to the primordial microorganisms that live in extreme environments.
So for them, actually, it's a great environment, it's a great food source, and basically a never running out food source because it's getting supplied from deep down there.
On Earth, there are microorganisms that can use asphalt for sustenance instead of water. Schultz-McCook is convinced that in Titan's lakes, there must be life forms that exploit methane in a similar way. Another scientist, Chris McKay, holds that the methane lakes on Titan contain creatures so unlike Earth creatures that they exceed our wildest imaginations.
Think of fish living in water and ask them to imagine a bird which lives in air. They probably can't conceive of an organism that is so much denser than the medium in which it lives. Fish move through water by floating. So they would imagine a bird must float in the air.
We humans live in an environment called Earth. We produce energy by causing oxygen and organic matter to interact. That is our lifestyle. But McKay is arguing that on Titan, life forms would be based on a Titan lifestyle that makes use of what's available on Titan. Titan's atmosphere contains minuscule amounts of hydrogen and acetylene. McKay thinks that there may be life forms on Titan that exist by deriving energy from the interaction of those two substances in a methane environment. McKay says that life could very well already exist on Titan.
So instead of being small and round, I would guess that a single-celled organism on Titan might be big and flat, like a sheet of paper, to maximize its contact with the nutrients in this thin soup. So it's living in an environment where there's not a lot of food. So it's got to access the food with big area. And maybe on this area, it has active molecules. So it's like a big flat sheet of paper with little traps on it to collect food. To that life form, that will be the normal environment.
It was not until the 21st century that Titan's thick veil was lifted. Now that we're getting a closer look, what new discoveries await?
So Titan gives us a whole new set of possibilities, and there are for sure perhaps hundreds, maybe millions of worlds like Titan around other stars. Do those have life? Titan maybe can give us some clues.
If life is found on Titan, humanity's view of the universe will surely change.
The best place for me in terms of finding another type of life would be Titan. Because if we find it on Titan, then we know that it really is too. It's not the same as us. When we go to Mars, we may find life on Mars, but we won't be sure that it's not the same life as Earth. So my best hope would be we find life on Titan, because then I know that we found two completely different types of life. Then I can go on to some other science problem.
There is only one body in space that we know of, other than Earth, that has a thick atmosphere and lakes. Titan. If life is found on Titan, it will instantly increase the possibility that life exists in many other places in the universe as well. we may not be alone in the universe. We may have many comrades. The quest to find out for sure continues. Clues to solving that great mystery lie hidden on Titan.
Perhaps life has gotten a foothold. But life as we know it requires water. How can scientists possibly find this miracle substance on planets light years away? Water divides our living world. Those with it prosper. Those without suffer. Remarkably, the water we drink today contains the same atoms as the water dinosaurs drank 100 million years ago. It's the same water that formed clouds over the early Earth 4 billion years ago. And every organism that has ever existed on Earth has used this single ration of water as the biochemical powerhouse that keeps it alive.
On Earth, all life requires liquid water to grow and reproduce. It's the common ecological requirement for life.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, actually interact with each other, form more complex chains.
It does it with charge. There's positive charges and negative charges separated between the hydrogen and the oxygen in H2O. Those charges break apart the hydrocarbons, the carbon-based molecules that persist everywhere in nature.
Now that's very rare. Hardly any other liquids do that. So liquid water is a natural starting place when you look out into the universe and say, what planets could possibly have life?
To understand how much liquid water is out there, astronomers must first calculate how common water is in all its forms. Amazingly, they find it everywhere they look.
Water is incredibly common. In its gaseous form, we see water vapor filling the space between the stars. We see it in clouds of material that are actually forming new stars and planets right now.
Since water is a fundamental building block of stars and planets, exoplanet worlds must surely have it in abundance. But if you're looking for life, you need to find liquid water, and plenty of it. To find it, astronomers take their cue from a fairy tale.
Everybody knows the famous story of Goldilocks and the Three Bears and the cup of porridge, where one was too hot, one was too cold, one was just right. When it comes to cooking up life like a porridge, you need to have an environment that's not too hot, not too cold, just right. And traditionally, we look for that at a certain distance around a star.
At first, astronomers based this magical distance, known as the Goldilocks zone, on the Earth's orbit around the Sun. But as they found more and more exoplanets, they've had to reevaluate the boundaries for liquid water.
There isn't a single distance. It depends on the brightness of your parent star. A dim star, you need to be closer. A hot star, very bright, you need to be farther away.
Scientists have calculated just how many rocky planets may lie within the Goldilocks zone of their stars. It comes out to over 30 billion potentially watery worlds. Even more remarkably, recent discoveries have shown us it's not just planets that can bask in the warmth of the Goldilocks zone. There may be moons painted blue with oceans too.
Most of the planets we're finding are big Jupiter-sized planets. However, a lot of them are orbiting roughly where the Earth is orbiting the Sun. So even if the planet that we're finding can't support life, it could have a moon with an atmosphere that could support life.
And the biggest of these rocky moons may resemble our home.
There could be billions upon billions of exomoons out there. and even perhaps countless paradises teeming with life.
David Kipping searches for exomoons by looking for double dips in the brightness of distant stars.
We look for exomoons in a very similar way to the way that we look for planets, by looking for them transit their host star. Now, if that planet had a moon, then we should expect to have one big dip due to the planet, and then one smaller dip either to the left or to the right due to the moon.
Habitable exomoons may play host to one of the most spectacular sights in the universe. Imagine a warm, rocky world, just like our own, with oceans and mountains. But in the sky, a massive ringed planet with a fiery sister moon shooting hot magma into space. Exoplanets, and now the vast potential of exomoons, hint at a galaxy filled with the possibilities for life. But a rocky surface and liquid oceans may not be enough. Biology needs the breath of life, air. Backlit by the sun, a halo appears around the Earth. A pale blue ring of light, our atmosphere, and we owe it everything. The Earth's atmosphere provides the gases that fuel the biochemistry of advanced life. But it also protects the oceans from the full fury of the sun's rays, preventing the water from boiling away into space. Without an atmosphere, there would be no wind, no rain, no fresh water, and probably no life.
Atmospheres are absolutely essential for life. Take a look at the planet Earth, and you realize that just like the skin of the apple preserves the apple, well, the atmosphere of our planet preserves the oceans and makes possible the presence of life as we know it.
Scientists, in search of living exoplanets, hope to detect the thin, gassy envelope that should surround these alien worlds. To do it, they're turning to the power of rainbows. In the same way that water splits sunlight into a rainbow, astronomers use instruments to split starlight into a band of colors called a spectrum. It's one of the oldest tricks in science, and one of the most revealing.
Several hundred years ago, scientists first began to take something like a prism and put it in front of their telescope. So they started taking the light from stars like the sun and actually spreading it out into a spectrum. And what they saw was kind of surprising. So instead of seeing a continuous rainbow of light, they saw that rainbow, but they saw these dark lines superimposed on top.
Each chemical element in the star's atmosphere absorbs different parts of the spectrum, creating signature dark bands.
For instance, up at the top, there's a pair of lines in the yellow part of the spectrum which are due to sodium.
Like a DNA profile for stars, spectral analysis has taught us almost everything we know about stars today. But these same lines may hide a marvelous secret: the faint signal of alien atmospheres, and perhaps also alien life.
So the challenge is that these planets are very small and very faint. So we can't actually go and directly measure the light emitted from the planet the same way that we go and measure this lovely spectrum for the sun. Instead, we have to rely on more indirect methods. So one indirect way of doing that is to wait until the planet passes in front of the star.
When the light of a star passes through an exo-atmosphere, the gases that surround the planet should stamp their own faint lines on the star's spectrum.
So as we watch the light from the star transmitted through that atmosphere, its atmosphere is going to act like a little filter So part of the starlight's going to pass through that atmosphere, and we're going to see that imprinting extra lines on it, which are due to the planet's atmosphere. So that change in the spectrum tells us something about the properties of the planet's atmosphere.
The one chemical astronomers most want to find is oxygen, because only life can produce enough oxygen to be easily detected. It's a so-called biosignature. The race is now on to find biosignatures in the atmospheres of rocky exoplanets. And while some groups look for rainbows indirectly, others are tackling the challenge head on.
27 to 29. All right, we're off.
Ben Oppenheimer is part of a team trying to take direct photographs of exoplanets using massive ground-based telescopes.
Awaiting instructions.
We're within minutes of taking our first long exposure, and I hope it's good.
The greatest challenge to imaging exoplanets is the blinding light of the parent star, which shines tens of millions of times brighter than the planet itself. The trick is to stop the light of the star from entering the telescope's sensors by blocking it, using a series of masks and lenses called a coronagraph.
Right now we're standing right underneath the telescope's primary mirror, and the light comes through a hole in the middle of the mirror and goes into this crazy box here, which is full of optics, motors, sensors, and electronics that all allow us to precisely control the starlight that's coming through the system.
Using state-of-the-art software, they manipulate the coronagraph to black out the unwanted light.
Under good conditions, we can actually carve dark holes into this image of the star so that we can see really faint things in those regions.
Coronagraphs present an intriguing problem, though. Errors within the optics produce tiny flares of starlight called speckles that look just like exoplanets. But Ben has come up with an ingenious way to tell speckles from planets.
So we've developed a technique where we exploit an aspect of speckles, which is that they change position in the image depending on what color you take your image at.
Image processing.
So Ben takes the same image of the star through different color filters and runs them like a movie. The speckles appear to move across the screen, but the planets stay stock still, allowing Ben to easily pick them out.
And so I'd like to point out that there is a little thing right here that if you watch for, you're careful, you'll notice that it doesn't move and the speckles are washing over it.
This stationary blob is a candidate exoplanet. And below it, and to the left, is a second. They both appear to orbit a star around 200 light years from the Earth. Just a decade ago, capturing an image like this through a telescope was unthinkable. But today, thanks to the ingenuity of astronomers like Ben, we have hundreds. And by analyzing the light from these distant worlds, scientists can work out their chemical composition and potentially the fingerprints of life.
At this point, we're studying much larger planets, gaseous things like Jupiter that most likely don't have any kind of life like we know it. But that's a first step. And we're going to fainter and smaller planets as time goes on as we develop this technology.
In the not-too-distant future, scientists may be able to simply scan a star for Earth-like planets and find the signature of life there.
We can look right at the light from a little planet around its distant star, and that opens up a whole range of possibilities for us to not just detect the planet, but to study the planet.
I mean, this all sounds like science fiction, but there is a reality to this. We have a scientific method to actually determine whether there is life on another planet.
Life is one thing, intelligent life, another altogether. That requires billions of years and a powerful force field like the one we owe our lives to every day. If an alien astronomer were to file a report on our home solar system, they might make a surprising observation. Because of all the 8 planets that orbit the Sun, they could easily conclude that 2, not 1, were suitable for life. It's an easy mistake to make, because the Sun has 2 planets within its Goldilocks zone, the Earth and Mars. Both planets have surfaces warm enough for liquid water to pool on. But while the Earth is blessed with warm, liquid oceans, Mars is dry and dead. The one crucial difference between these 2 planets could be the key to finding truly habitable exoplanets: a magnetic shield. Our Sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away. And without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. You know, if there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
So where does the Earth's magnetosphere come from? And why doesn't Mars have one? Actually, in the past, both Earth and Mars had magnetospheres, but Mars lost its around 4 billion years ago, and with it, the potential for life. Both the Earth and Mars were born into a realm of violence. Asteroids smashed into their surfaces, turning rock and metal into a molten mass. As they started to cool, a solid crust formed on the surface. But the molten metal below churned as the planets turned, inducing a magnetic field which rose high up above the surface of both planets. At the same time, active volcanoes pumped gas into the space around each planet. Protected by the newly formed magnetic field, these gases built up into thick atmospheres, creating the air pressure for liquid water to run on the surface. For over 100 million years, both Mars and Earth were warm, wet paradises, primed for life to take off. Then, quite suddenly, Mars's magnetic protection disappeared. The solar wind blew its atmosphere into space, and its oceans boiled away, leaving the dry, sterile red rock we see today.
Mars' fundamental problem is that it's smaller than Earth. And because it's smaller, the internal core of Mars cooled down and solidified. And once it becomes a solid metal, there's no more magnetic field. The magnetic field shuts off, essentially, and the atmosphere, therefore, is vulnerable to both energy and radiation from the sun and the rest of the galaxy, and probably just blew off. Whatever life was on there, at least on the surface, is now completely exposed.
All rocky planets will one day lose their magnetospheres as their cores cool and turn solid. So, to know if an exoplanet is alive, you need to work out if its magnetosphere is still active. But magnetospheres are tough to measure because they are unbelievably weak.
The Earth has a magnetic field of approximately half a Gauss, which, when you think about it, is actually really weak. Our fridge magnets are about 100 Gauss, so they're much stronger.
Exoplanets are too far away for us to measure such weak magnetic fields directly. But there is an indirect method. When electrons in the solar wind interact with a planet's magnetosphere, they emit radio waves that beam out into space, turning the planet into a giant radio beacon. Astronomers like Evgenia hope to use these signals to spot habitable exoplanets. Not only that, the frequency of the signal should also tell her how big the planet is.
If we're looking for the magnetic signature in the radio waves of a giant planet, say a hot Jupiter, we expect it to have a strong magnetic field, and therefore it would have a high frequency, and around 100 megahertz, kind of where the limit of this radio is. However, a weaker field like Earth's requires us to go down to lower and lower frequencies. So instead of 100 megahertz, we go down to 10 megahertz.
But hunting for exoplanets at 10 megahertz presents a unique challenge. Because the Earth's own magnetosphere creates a deafening radio roar at that frequency. So to find alien Earths using radio requires a dish in space.
When we want to look for magnetospheres of extrasolar planets, we really need to get outside of the Earth-Moon system in order to get away from all the radio frequencies that are bouncing around the Earth.
With a slew of new technologies and upcoming technologies, scientists are edging ever closer to the ultimate prize, finding a second Earth.
I wouldn't be surprised if we have that data about an Earth and about life on it around another star in 10 or 15 years. I'm hoping to see that soon.
Using shadows, rainbows, and now radio, we finally have the tools to detect a planet just like our own. But in the rush to find the Earth's identical twin, are we missing something big? What if Earth is an outlier, a freakishly lucky place on the very fringes of habitability? Could there be another kind of planet out there, even better for life? For years, astronomers have scanned the heavens for planets that could sustain life. They've based their search on the Earth, seeking the exact same conditions and the exact same size.
I think right now there's a huge focus to finding Earth-like planets. Now, whether or not there actually is life there, that is another question altogether.
But after 20 years of searching for an Earth clone, the exoplanet hunters may be about to switch targets. Recent observations have revealed a brand new class of planet, and it's one that may eclipse our own home.
We've learned something in the last few years that really shocked us. With the Kepler spaceborne telescope, we have found hordes of planets that are a little bigger than the Earth. We never imagined that there would be such planets. In fact, in our own solar system, there are no planets between the size of the Earth and the next largest planet, that of Uranus and Neptune.
Astronomers call these mysterious planets super-Earths.
Super-Earths are about 3 to 5 times the mass of the Earth, and there's nothing like that here. We don't know what they're like. It's an entirely alien sort of planet.
In just the last few years, astronomers have begun to imagine the conditions on this new class of planet, and they've come to a startling conclusion. Super-Earths could be super-habitable.
There are probably planets out there that are even more hospitable for life. Planets that have even more chemicals necessary to create the organic materials that create life, conditions that make it more likely to get life off the ground.
Imagine a rocky planet, twice the size of the Earth. Dramatic volcanism on the surface betrays a vast heart of fire that beats within its core.
We expect that a heavier Earth will be more geologically active, that the increased amount of geothermal heat within the super-Earth will lead to stronger motions of the magma underneath the crust.
Belching volcanoes dot the surface of this super-Earth. Their gases feed a super-thick atmosphere and help to regulate a super-stable climate.
many times life on Earth was nearly extinguished. For example, once upon a time the Earth was snowball Earth, completely covered in ice. Maybe in these other planets, there are Earths in which snowball Earth never happened, that the climate was always stable and temperate.
The grip of gravity is 3 times stronger here than we're used to. It pulls mountain ranges down to 1/3 the height they'd be on Earth. Gravity also flattens the ocean bed, making shallower seas filled with volcanic island chains. And the nutrient-rich waters that surround these archipelagos provide the perfect conditions for life.
In these other planets, perhaps they have conditions which would make DNA get off the ground much earlier and flourish much more quickly.
Finally, our super-Earth may be protected by a supermagnetosphere.
The magnetic field strength is a condition both of the mass of the planet as well as its rotation speed. And so it is quite likely that a planet that is a couple of times bigger than the Earth's would be able to develop a stronger magnetic field, may shield the planet even better than our magnetic field shields us.
Having a stronger magnetosphere would be a distinct advantage for life on a super-Earth surrounding the Milky Way's most plentiful kind of star, the M dwarf, or red dwarf star. Red dwarf habitable zones are much closer in than the Earth is to the Sun because their host star is so dim.
It's as if you took the terrestrial planets in our own solar system and zapped it with a shrink ray gun and shrunk them down to orbital periods that are less than about 30 days, meaning that they're very close to their stars.
Some astronomers believe these planets are at risk from solar activity, such as deadly flares. But a super-Earth with a super-protective magnetosphere may well resist these deadly rays, allowing life to flourish under a psychedelic sky full of swirling auroras.
If one was standing on a super-Earth, we would see the aurorae come down to lower latitudes. You might get different colors. If I had the opportunity to travel to one of these exoplanets, I would snap that up pretty quickly.
Most intriguing of all, if life does exist on a red dwarf super-Earth, it could be home to the longest-lived civilizations in the entire universe.
The advantage of the M dwarfs is that they last for much longer. And if you had a super-Earth then, keeping a strong magnetic field, going for billions and billions of years, especially now around a red dwarf that is going to exist for billions and billions of years. You might be in that perfect system where life can exist and evolve into even more complex beings than us.
We're getting so close. Our local neighborhood of stars teems with red dwarfs, bursting with the potential for advanced life. But there are also cosmic killers out there, lurking in our galaxy, primed to wipe out life on a regular basis. Is anywhere safe? The exoplanet revolution is in full swing. The Kepler Space Telescope has scanned our local neighborhood of stars for planets, and it's found them by the thousands.
For a long time, we didn't know if the other stars in our galaxy had planets. And for thousands of years, there was no way to answer that question. Finally, now with modern technology, we can do that. And to our surprise, we found they are extremely common.
From Kepler's small sample, astronomers believe there could be tens of billions of rocky, Earth-like planets throughout the Milky Way, where life may already be thriving. But how many of these countless worlds has held on to this life long enough for intelligence to evolve? The answer, surprisingly, may depend on a planet's galactic zip code.
The universe is not a happy, safe place. The universe wants to kill us. It's incredibly violent out there. There are solar flares and supernovae and black holes and colliding galaxies and all these really amazingly dangerous and violent events. It's actually kind of amazing that we're here at all.
In order to develop advanced, intelligent life, an exoplanet may have to avoid these cosmic killers for over 3 billion years.
If we look at the history of the Earth, the first thing that happens that's important is the origin of life, right away, very quickly. But then, nothing for a long time. You have nothing but microbes stomping on the Earth.
For the first 2.5 billion years, the Earth was ruled by single-celled goo. Multicellular life has only been around for 1 billion years. Fish for 500 million. Mammals for 200 million. And modern humans have only walked the Earth for the last 200,000 years. The lesson is clear. It takes a long time to cook up intelligent life. But most planets in the Milky Way don't have that kind of time. Astronomers believe that a planet's position within a galaxy may determine if it gets hit by global extinction events.
There's an idea of a habitable zone for a galaxy, and it's in analogy to the habitable zone around stars.
Stars too close to the galactic center are in the firing line from their violent neighbors, which frequently blast them with deadly high-energy radiation.
In the middle of a galaxy, we have a lot of bright stars and young stars and maybe even supernova going off. And so there's a very harsh radiation field. That's not good for life.
Fired up by the supermassive black hole that sits at the center of the Milky Way, this cosmic kill zone stretches out around 8,000 light years from the galactic center and extends out along the densely packed spiral arms. Any planets that exist within this zone are likely to have their surfaces regularly scrubbed clean of life. Fortunately for us, our home star, the Sun, sits in a relatively empty, quiet zone between two of the galaxy's spiral arms.
So there's this idea that there's a band in the middle of the galaxy that's the galactic habitable zone, where you don't have too many stars going off, you don't have too many supernovae, so it's quiet in that way. Those might be great places for complex life.
These green zones are like the suburbs of the Milky Way galaxy. They're sheltered from the worst of the galaxy's radiation. It's here that Earth-like worlds will have the luxury of long, uninterrupted periods for life to take hold and develop into more complex forms, and eventually, perhaps, intelligent life, like us. The galactic habitable zone is no more than a fledgling theory, but if it's true, it reduces the number of places where advanced life could flourish in the Milky Way. The good news is those places should be near us, and aliens more likely to be on our doorstep. And with our technology getting better every day, it surely won't be long before we find them.
I think in 20 years' time, I'm going to be able to look up into the night sky and say there really is another place I could stand like this and feel at home.
Suddenly we humans will realize for the first time that there are other cultures, other civilizations, probably other religions out there among the stars, and we are just one member of a grand galactic tribe.
To have cousins that we one day may communicate with seems to me to be potentially one of the greatest developments that humanity will ever experience. And if that isn't worth doing, I don't know what is.
At the dawn of the 21st century, space agencies in Europe and America began making plans to land the first humans on Mars. But manned missions to the Red Planet have been proposed before. For some, Mars holds the answers to mankind's future in space. Others say Mars is too far, too dangerous, and too expensive for humans to explore. And in a world torn by troubles, some say there is no need, or will, for mankind to reach into space anymore. More than 30 years after the last Apollo astronaut walked on the moon, the American manned space program seems to have lost its way, unable to reach beyond even low Earth orbit.
We've got a problem. NASA has been literally going around in circles with its space program for the past 30 years.
Astronautical engineer Dr. Robert Zubrin has been arguing for years that sending humans to Mars is the mission the space program needs.
It's time that we set goals for NASA that were worthy of the risks of human spaceflight. Mars is the next logical step in our space program. It's the challenge that's been staring us in the face for the past 30 years. It's the planet that's most likely Earth. It's the planet that has on it the resources needed to support life and therefore someday technological civilization. It's the planet that will provide us with the answer as to whether life is prevalent in the universe or exclusive to the Earth. And it's the planet that will give us the critical test as to whether humanity can break out of the planet of our birth and become a spacefaring species.
In the early 1990s, Zubrin was the head of the Mars Direct program at Martin Marietta Astronautics. His team developed a mission to Mars that could be done at a fraction of NASA's projected costs. Using only existing technology, Zubrin argues that the first steps on Martian soil could be made within 10 years.
There is absolutely nothing in this that is beyond our technology.
We are not ready to send humans to Mars right now. We don't know how to keep them alive. There are people out there who say we can go to Mars tomorrow. One of my requirements, one of NASA's requirements, is that if we send humans to Mars, we bring them back alive.
For the past 15 years, Zubrin and his colleagues have waged a campaign to convince society and the political class that humans on Mars should be the goal for NASA now. This is the story of our cold neighboring planet and the debate over whether man's fate is tied to the red world. It's the story of an engineer's journey and the battle of ideas over which direction in space will truly benefit mankind.
We're at a crossroads today. We either muster the courage to go or we risk the possibility of stagnation and decay.
The victor in this debate could determine the fate of mankind. Will we become a spacefaring species? Will we live on more than one planet? In the winter of 2003, the Chinese put their first taikonaut in space. The Chinese Space Administration plans to begin a manned program of moon exploration by 2017. The European Space Agency has outlined a plan for humans to the moon by 2024 and to Mars by 2033. And the Russians, building on years of experience, are conducting tests for long-duration Mars missions. In America, with the impending retirement of the shuttle fleet and the completion of the International Space Station, the Bush administration announced in 2004 the Constellation Program,
On the moon.
a plan that would return Americans to the moon by 2020. But the program was never fully funded and was eventually cancelled. In 2010, the Obama administration announced its vision for NASA and human Mars exploration.
By the mid-2030s, I believe we can send humans to orbit Mars and return them safely to Earth. And a landing on Mars will follow, and I expect to be around to see it.
With a new timeline for humans to Mars sometime after 2035, and with administrations changing every 4 or 8 years, it is far from certain that such a plan will be realized. 20 years earlier, the first President Bush also proposed a long-term human exploration program, under great fanfare. The program quietly died in Congress a few years later.
If you want to go to Mars, you cannot do it in 30 years. You can't do it in 20 years. You've got to do it in 10 years or less from program start, or you're more or less guaranteeing political failure.
To date, only the Apollo moon program, which was announced in 1961 and had men on the moon 8 years later, has succeeded in getting astronauts beyond low Earth orbit.
I was 5 when Sputnik flew. And while to the adults, Sputnik was a terrifying event, to me, as a child who was already reading science fiction, it was exhilarating, because it meant that this possibility of a spacefaring future was going to be real. And I was 9 when Kennedy gave his speech committing us to the moon.
To go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I grew up during the 60s when it was Mercury, it was Gemini, it was Apollo. Every month, NASA was doing something more impressive than in the month before. We were going to be on the moon by 1970, Mars by 1980, Saturn by 1990, Alpha Centauri by the year 2000. We were moving out, and I wanted to be part of that. And so I got myself a scientific education. But then, in the early 70s, it's all collapsed. We achieved the first part of that program, moon by 1970, but the Nixon administration shut down the rest, and we did not move out into space. And for a while, I accepted that, grudgingly. I became a science teacher. But then in the early 80s, something hit me, and I said, I'm not going to accept myself doing less than what I had dreamed of doing when I was a boy.
Zubrin went back to graduate school, getting advanced degrees in engineering and aerospace. He then went on to work at Martin Marietta, which later became Lockheed Martin, designing interplanetary missions. It was here that Zubrin's obsession with the red planet began to take hold. While at Martin in the 1990s, Zubrin and his colleagues developed a plan for sending humans to Mars that changed NASA's thinking on the issue. But the plan has languished on the drawing boards ever since. Now, as president of the Mars Society, Zubrin is at center stage in the debate over the future of manned spaceflight. Known as a smart, visionary scientist, he has authored several books on exploring space and is the self-appointed spokesman for the possibility of colonizing Mars.
Mars is where the future is. Mars is the closest planet to the Earth that has on it all the resources needed to support life and therefore technological civilization. It has water, it has carbon, it has nitrogen, it has a 24-hour day, it has a complex geological history that has created mineral ore, it has sources of geothermal energy. Mars is a place we can settle.
One reason for such optimism over a frozen world like Mars is evidence that 2 billion years ago, Mars was a much warmer and wetter place.
We think that at one time in the ancient past, Mars was very similar to the condition of early Earth.
This Martian warm age lasted for over 1 billion years and could have been a suitable environment for the development of life.
If we go to Mars and find evidence of a second genesis on Mars, I think we can conclude that the universe is full of life. We can probably conclude that on some planets that life evolves to more complex forms, and I think we'd be reasonable to conclude that intelligence could also emerge on some planets as well. It really does answer the question, are we alone? And that to me is a question that transcends science. It's a philosophical, societal, as well as scientific question. To me, that's the big prize. That's why Mars is interesting. That's why human exploration makes sense.
Space programs are often criticized for the huge sums of money they require. Although the American space program is less than 1% of the federal budget, a human mission to Mars may have to wait for better times.
There are those who say that we have many problems to deal with here on Earth, and we need to postpone ventures such as the human exploration on Mars until these problems are solved. Well, there were many problems in Spain in 1492, and there still are. There are problems that need to be dealt with here on Earth, and should be dealt with. But we also have to think of the future. We also have to think about opening up new volumes in human history. I believe that it's essential for a positive human future that humanity expand into space. The greatest value that we got out of Apollo was the creation of intellectual capital through the inspiring of millions to go into science and engineering to be part of the great adventure of human expansion into space.
There's a phrase that happened with the Apollo program, which was, if we can go to the moon, we can. And then everybody's filled in whatever they were interested in. Build mass transit, cure cancer, do this, do that. The point is, it did give us a sense that we could accomplish great things. It did bring out the best of us.
We excited a generation of engineers and scientists. The generation that built the computers and cell phones and all the technology everybody uses today and takes for granted.
If we set humans to Mars as our goal, we'll get millions of new scientists that will create new inventions, new industries. This is the enormous payback, and we can get it if we set the kind of challenge that will inspire the youth.
To Zubrin, civilizations, like people, thrive on challenge and decay without it.
We have everything we have today because of our predecessors who had the courage to leave the world of the known and go out into the wilderness and build new cities. And if we stop being people like that, then we will hand down much less to our posterity than our ancestors handed down to us. So there's the choice in life. One either grows or one decays. Grow or die. I think we should grow.
History proves that we have never lost by pressing the limits of our frontier.
In the summer of 1989, the first President Bush announced the Space Exploration Initiative, directing NASA to draw up long-term plans to get humans back to the moon and begin developing a program of manned Mars exploration. At Martin Marietta, Zubrin and his colleagues looked forward to moving NASA's space program outwards after 2 decades in low Earth orbit.
Of course, we were very excited when Bush made his call saying that he was making a national commitment to implement such a program.
NASA assembled a large team to take on the space initiative. In 90 days, the team developed a 30-year plan that required an enormous buildup of space infrastructure.
What the NASA bureaucracy decided to do was basically design the most complex mission they possibly could in order to make sure that everyone's pet technology would remain mission critical, which is the exact opposite of the correct way to do engineering.
First, NASA would triple the size of the planned space station and add enormous hangars, as well as free-floating fuel depots, checkout docks, and cruise stations. Then, on the moon, they would construct more shipbuilding facilities, bases, and depots. Next, the moon crew would construct the Mars ship, a huge craft dubbed by its detractors as Battlestar Galactica. This ship would carry everything to Mars over an 18-month flight. Once in Mars orbit, a small group would descend to the surface, spend a few days, then plant a flag in the ground and go home. plan became known as the 90-day report.
To those of us at Martin who had been engaged in designing Mars missions, when they saw the monstrosity of complexity of the 90-day report, we were dismayed, and it was readily apparent to anyone with any insight that that program would fail politically.
The plan was submitted to Congress. The estimated cost, $450 billion. The legislators went into sticker shock. This would have been the single most expensive program for the United States since World War II. By the end of 1990, Congress had refused all requests for SEI funding. When the realization came that SEI was doomed, Zubrin wrote a memo to his colleagues at Martin Marietta, outlining his problems with the NASA plan and arguing for a more direct approach. Zubrin favored launching a Mars mission directly from the surface of Earth, using only existing rocket technology. This negated the need for a lunar base and avoided the complexity and cost of building ships in space. He also objected to NASA's plan for a short surface stay on Mars, a mission that would amount to little more than a flag and footprints exercise. To Zubrin, we were going to Mars to explore and develop a new world. To maximize surface time, Zubrin proposed using a faster flight path, known as a conjunction-class mission. This would mean a crew could arrive on Mars after only a 6-month journey. They would then remain on the Martian surface for a year and a half. This would give the team time to explore a wide area and conduct detailed research about the planet. Then, as the Earth return window opens, the crew would launch from Mars for the 6-month trip home. Zubrin was convinced that a simplified, more robust and cost-effective mission could be designed using these principles. Along with several like-minded colleagues, Zubrin decided to ask management at Martin to allow them to design alternative Mars missions.
The management approved that, and we formed a team, what was known as the Scenario Development Team, of just 12 people from the whole very large Martin company.
One team member, whose thinking was closely aligned with Zubrin's, was David Baker.
I went off to my office and said, all right, how would I do a Mars mission if I had to pay for it and I had to go on the ride? And I said, well, it's going to be simple. There's going to be no on-orbit assembly. I really tried to take everything out of the mission that didn't absolutely need to be there.
While the rest of the team focused on longer-term, more traditional mission plans that required on-orbit assembly, Zubrin and Baker decided to collaborate on a mission that could be done near-term.
We decided to do Mars the way Lewis and Clark did America. Okay? Use local resources, travel light, live off the land.
Zubrin and Baker were convinced that a Mars mission could be launched directly from the ground. The other team members felt this was impossible, that the weight of the rocket fuel required for a round trip to Mars was so enormous it would render the launch ship impossibly heavy. To solve this problem, Zubrin was exploring a radical idea that had been kicked around the aerospace industry since the 1970s. The idea was to produce a methane-oxygen rocket fuel directly from the Martian atmosphere. It was a relatively simple and robust chemical engineering procedure that was done commonly in the 1800s, the era of the gaslight. If the idea worked, astronauts could land a relatively light ship with empty tanks. They wouldn't have to ship all the fuel with them for their return trip. This would radically lower their size and weight. The only problem was methane-oxygen fuel requires a hydrogen component. Hydrogen exists on Mars in the form of H2O, but water may be difficult or impossible to extract from the Martian environment.
Really, the hydrogen was only 5% of the total weight of the methane-oxygen propellant being manufactured. So if you just say, okay, we won't be pure, we won't get all of the propellant from Mars, we'll just get 95% of the propellant from Mars. The other 5%, the hydrogen, we'll just bring from Earth.
Another fundamental resource that could be extracted from the Martian environment is oxygen. A second processing unit could separate oxygen molecules from the thin carbon dioxide atmosphere, providing breathable air for a Mars crew.
If used intelligently, the same resources that make Mars interesting are precisely what could make it attainable.
Baker and Zubrin had greatly reduced their mission mass, but they still found their ship was too heavy and would require 2 launches and assembly in space. Then Zubrin hit on an idea.
Well, one of the key events of the Mars Direct development was one morning Bob burst in my office and said, "I've got it."
The idea that I finally hit on in 1989 was that we would split the mission up into 2 parts, and we'd send the return vehicle out first with its own return propellant plant. So the propellant would be made on Mars before the first astronauts ever left Earth.
With 2 separate direct-to-Mars launches, a human crew would have a fully fueled ship waiting for them on the surface of Mars before they ever left Earth. So Zubrin and Baker had come up with a plan that seemed to accomplish all of their goals. It was relatively inexpensive, development time was short, they could use existing technology, and it allowed for a long stay on the Martian surface. They dubbed their idea Mars Direct.
SSC disconnect enable on. 35. Electronics go. Hydraulics go.
Aboard an Ares rocket is the Earth Return Vehicle, or ERV. No one is aboard this ship. It will pave the way for the astronauts who, years later, will use the ERV to return to Earth.
1. And liftoff.
On its second day, the ERV deploys a small nuclear power reactor. The reactor powers a chemical plant inside the ERV. The plant will produce the methane-oxygen rocket fuel for the launch home. Nearby, a second robotic rover is guided to a pre-picked landing site for the human crew. It places a radar transponder to help guide the astronauts in. The long journey to land a human being on Mars begins.
3, 2, 1, engine start.
Carrying the most skillfully assembled flight team in history, 4 astronauts begin their 2.5-year mission to the Red Planet. This will be the first time a human has gone beyond the Earth-Moon system, 250 million miles farther than any person has ever been. To counter the health problems of zero gravity and to fully acclimate the astronauts to Mars, the ship will deploy a weighted tether attached to the last stage of the spent rocket booster. By thrusting the ship into a rotational spin, the counterweight of the rocket will create centrifugal force and thus artificial gravity. The crew will be able to live with their feet planted firmly on the floor during their 6-month transit. But the HAB is not entirely alone on its journey. Just ahead of it is a second ERV, identical to the first. Launched just a few weeks prior to the HAB, it will prepare the way for a second human crew that will follow 2 years later. It can also function as a backup for the first mission, if anything should go wrong. the 6th month of the flight, the crew will gaze upon an alien world. This is the new frontier.
Oh, spectacular. Just spectacular.
After days in orbit and satisfied with the landing conditions, the crew will receive final word from Mission Control on Earth.
All systems are go for entry, descent, and landing. 3, 2, 1.
It will be a tense 40 minutes before people back on Earth get the signal from Mars and know if everything has gone well.
Okay, 75 feet. Car's looking good. Down a half. 6 forward. 60 seconds. Lights on. Forward. Forward. 40 feet down. 2.5. Big shadow. 4 forward. Drift into the right a little. 30 seconds forward. Contact light. Okay, engine stop.
We're seeing it on the LTP. We're on Mars, everybody.
For more than 500 days, the astronauts will live on Mars and embark on one of the greatest journeys of discovery in the history of science. Will they find life? Or the fossilized remains of past life? Such a discovery could tell us whether our solar system has seen more than one genesis, and answer the ultimate question: are we alone? In any case, these explorers will be learning how feasible the colonization of Mars really is, and whether or not mankind has a future among the stars. Then, when the time comes and the window for Earth return opens, the crew will climb into their Earth return vehicle and head home. They will arrive home heroes, the first to stretch the limit of man's expanse from one planet to another, their names added to the list of great explorers of new worlds. In their footsteps, others will follow. What began as a trickle is free to rise into a deluge of humankind, sweeping over a once barren land and transforming it into a viable new world. When Baker and Zubrin presented Mars Direct to their bosses at Martin, they expected the worst. To their surprise, management was excited about it. They liked the fact that everything needed was relatively simple and near-term.
As time went on, Martin Marietta embraced Mars Direct as their creation and put Bob and I on an airplane to several NASA centers to present Mars Direct and try to build some momentum for it.
Baker and Zubrin flew to the Marshall Space Flight Center in Huntsville, Alabama. This had been one of the original design hubs for the Apollo moon landings, but recently many of the engineers had become demoralized by the failure of NASA's SEI program. Tag team style, Baker and Zubrin presented their alternative mission architecture. The response was thrilling. The old-school Apollo crowd embraced it. This was a plan that actually made sense and was within reach.
Baker and I gave a number of briefings. The first was at the Marshall Space Flight Center. Next was at Johnson. These people were incredibly excited.
Over the next few weeks, Zubrin and Baker were flown around the country, pitching to all branches of NASA. And everywhere they went, the response was electric. The plan was standing up to scrutiny, and groups all over NASA were converting to Mars Direct. Their tour culminated in a public presentation to the National Space Society. The crowd gave the two aerospace engineers a standing ovation. week later, the story was in newspapers around the country. But a counterattack was beginning to form within NASA. The space station teams and many in the advanced propulsion groups were against the idea. Since Mars Direct didn't need their programs, they felt under threat. As quickly as doors opened for Zubrin and Baker, they began to close.
NASA didn't want to pursue a Mars mission at that time. They didn't want to be derailed by a bunch of Mars fanatics that thought that their idea of what NASA should do should overwhelm what NASA thought NASA should do.
What we did in Mars Direct was literally come up with the leanest solution, the one that involved the least spending on an assortment of technologies and infrastructural elements, including, for example, we made no use whatsoever of the International Space Station. And so people involved in all those programs were very upset because we were showing that you could go to Mars without their program being required. And they felt that we were de-justifying them.
The NASA administration rejected Mars Direct. The two engineers were outsiders again. But Zubrin remained determined.
Bob had grabbed hold of it, and I could see that it was his, and no matter what I did, he was going to do what he was going to do, and he was going to be a proponent for it and push it, and I really saw my role sort of evaporate. It's a little bit like being a dim planet next to a bright star around him in terms of his enthusiasm, and you really can't compete with that. All you can do is decide how you're going to deal with it.
By February 1991, Baker quit Martin to start his own firm. Zubrin battled on. For the next year and a half, Zubrin tried to get NASA to pay attention, giving speeches, writing papers, but Mars Direct's time seemed to have passed. But then in 1992, a new administration came into power at NASA, and Zubrin saw a second chance.
I was invited to brief Mike Griffin, who was the Associate Administrator for Space Exploration in charge of the whole Space Exploration Initiative. He immediately became a very strong supporter of Mars Direct.
But before the engineers at NASA would take another look at Mars Direct, they wanted Zubrin to prove that producing rocket fuel on Mars could work. They gave Martin Marietta a small budget to do an experiment. Zubrin and his team built a machine called the In Situ Propellant Plant. It could take carbon dioxide, the dominant gas in the Martian atmosphere, combine it with a little hydrogen, and produce a methane-oxygen fuel.
We did it in 3 months with a very small team. We built a plant that was 94% efficient, and no one who actually participated in that effort was actually a real chemical engineer. They were all aerospace engineers, like me, who were simply dabbling in chemistry in order to prove to NASA that 19th century chemical engineering really worked.
With the experiment a success, the administration had Zubrin give detailed briefings of the mission plan to the engineers at the Johnson Space Center. They liked it, but had some problems. Dave Weaver was the lead mission architect.
There were a number of things that we were concerned about with Bob Zubrin's mission. First of all, we thought his estimates of mass were probably too optimistic. Didn't have sufficient margins for a variety of things, not the least of which would be things like provisions for the crew, the amount of water that would be required. We thought his ascent vehicle was very large, which meant his power requirements, his propellant requirements were much larger than needed to be. His trip times out were too long, and that for very little effort you could get them shorter. The other problem was the size of his crew. He had a 4-person crew. I think virtually every study that's been done says that a 4-person crew for a 3-year type of mission is probably not realistic.
Weaver took Zubrin into his office, and the two men worked out compromise mission architecture. First, Weaver wanted 3 launches for every mission instead of 2. The first year, 3 ships would launch: a MAV, Mars Ascent Vehicle, an unoccupied HAB, and an ERV, Earth Return Vehicle. The HAB and MAV would land on the surface and begin producing fuel for the return flight and air for the crew. These craft would spend 2 solitary years on Mars, allowing NASA to test all of the systems before sending a human crew. Then, in the 3rd year, 3 more ships would launch, this time with the HAB occupied by astronauts. The other 2 ships are for a future mission, and less needed as a backup for this crew. Once on Mars, the team could also utilize the first hab. Then, after a 1.5-year stay, the crew would climb aboard their small capsule and rendezvous with the return ship. This ship would carry them back home in a roomier environment than Zubrin's ERV. Zubrin called the plan Mars Semi-Direct. NASA called it the Design Reference Mission.
They had a larger crew than we had. They had bigger ships. They had more equipment. They had heavier equipment. So they had to do the mission in 3 launches instead of 2, but it was done with the same principles of Mars Direct.
The plan was subjected to the same cost analysis that tagged the 90-day report with a $450 billion price tag. The Design Reference Mission came back at a fraction of the cost, $55 billion. Spread out over 10 years, it could be done within NASA's existing budget. The plan made the cover of Newsweek. Here was a mission architecture that was affordable and could be done today with existing technology. But NASA's astronauts have not left low Earth orbit since. With the completion of the International Space Station and the retiring of the Space Shuttle program, a debate rages over the future of space exploration. Should NASA continue to focus on low Earth orbit, developing technologies for the future? Or should NASA have a goal, like it did in the 1960s with Apollo?
The way we got to the moon was by a presidential imperative that demanded that NASA get to the moon within a decade. So NASA was forced to sit down, design a plan for how to do that, and then fly the mission. Since that time, without the presence of a driving imperative, we engage in basically a random set of constituency-driven programs which are justified ad hoc afterwards by the argument that they could prove useful at some time in the future when you actually have a plan to go somewhere.
I think NASA has focused on a steady process where the government can't just pull the plug on their funding. I think the Apollo cancellation was very traumatic for NASA, and it really transformed NASA from what it was in the 60s to more of what it is now. If you have a singular program like going to Mars, then it is very vulnerable to having its funding pulled.
NASA must be destination-driven. It is the only thing that allows the agency to be productive. NASA was 100 times more productive when it was destination-driven than in the period that it has not been. And we have stagnated in NASA since 1973. 30 years, more than a generation, has been wasted. The American space program's been stagnant for 30 years. There's a once-in-a-generation shot right now to get it moving again by giving it a goal that'll take it somewhere. So the stakes today are high. And if you ask me if I am nervous right now, I am.
Dr. Zubrin.
Why is NASA stuck in low Earth orbit? The problem with NASA's lack of current achievement is not money. The problem is lack of focus, it's lack of a goal. It shouldn't be humans to Mars in 50 years. It should be humans to Mars in 10. We can do this. We do not need gigantic nuclear electric spaceships to send people to Mars. That is pork, it's nonsense. The primary question I get from the American people is, why aren't we doing this? There's a big sense of disappointment, almost verging on a sense of betrayal. The purpose of spaceships is to actually travel across space and go to new worlds, not to hang out in space and observe the health effects from doing so.
Dr. Zubrin, in your testimony, you were very passionate, but you also were mad. You're mad we haven't done this, or that this vision has been stolen from a generation?
I guess you could say that. It's like Columbus coming back from the New World and Ferdinand and Isabella saying, so what, forget it, burn the ships. Okay, that's what has happened in this country. We've won our point that there needs to be a destination. The point we need to win on now is that the destination needs to be Mars, and it needs to be soon.
The movement to send humans to Mars in the near term began at the University of Colorado in 1978. A graduate student in astrogeophysics named Chris McKay gave a small seminar on the possibility of introducing life to Mars.
I got interested in Mars in graduate school. I entered graduate school the same year that Viking landed on Mars and sent back these images, and it sent back data that showed all the elements needed for life are here on this planet, and yet there's no life here. I thought, oh, that's odd. It's sort of the lights are on and nobody's home. And I thought, well, that's curious. So some of my other grad students and I, we sort of got together to talk about, well, if there's no life on Mars now, could we put life there? And that evolved also into the question, well, maybe there was life in the past, and so we could find fossils, evidence of it. Well, how would you do that? Well, you do that by sending people there.
Together with fellow graduate students, the group decided to put together a small conference to discuss the matter of human Mars exploration.
We basically just started a forum. We invited everybody from all the NASA centers and from all the universities that were involved in it, and they all came. And it really was, in retrospect, I realized a very important step toward building a consensus for human exploration of Mars.
In 1996, I published my first book, The Case for Mars, and the response was phenomenal. I got 4,000 letters from all over the world. I had Parisian bankers and 12-year-old kids in Poland and firemen from Saskatoon and astronauts, and they're all writing me and saying, how do we make this happen?
Bob Zubrin came to the third Mars conference and got very much involved. And he was willing and interested in forming a society, forming a group and organizing.
He said, look, if we could pull these people together, if we can get them to work together, we could have a force that could actually make humans to Mars happen.
The group formed the Mars Society. Robert Zubrin became the president. They held their first convention in 1998.
The convention was just magic. We had no idea how many people were coming. They were there not just from the United States and Canada and Europe. They were there from Israel. They were there from Mozambique. They were there from New Zealand. It was astonishing.
Since its inception, the Mars Society has attracted members worldwide. Derek Shannon is the head of the Southern California chapter. He's met with political leaders from all over the country.
If you make them look at the whole Mars vision in historical terms, it becomes a much easier sell. How will the Martians remember our century? They're probably not going to remember our deficit, our wars, our health care. Those will be footnotes. What they'll remember is that out of all of human history, there came a generation that decided to take this amazing step out into space. And if you tell politicians that they're the ones whose names actually get to be remembered, that's when, hopefully, the space program starts going somewhere.
In order to further the knowledge necessary for a manned mission to the Red Planet, the Mars Society has been building research stations around the globe, all of them based on the design of Zubrin's HAB module. Most recently, the Society set up a desert research station in Utah. Here, international researchers and aerospace students come to do experiments under the harsh desert conditions and learn what's necessary to keep a Mars crew alive and productive.
Basically, what we're doing here is undergoing analog studies. Crews of up to 6 people at a time come together to live in a full simulation environment for up to 14 days. So what that means is every time we go outside the HAB, people have to don spacesuits. They have to depressurize. When we go outside, they're called extravehicular activities. They can only be of a certain duration due to the air supply. We have to recycle all our water and basically have our own food as well.
It's great to fantasize, but it's another thing when you have to put it together, when the nuts have to fit the bolts.
Like the Apollo missions to the Moon, sending human beings to Mars will mean putting people in harm's way. There are many dangers in outer space, and many things could go wrong. A serious equipment breakdown could doom the crew to their deaths. Some argue that the risk of failure is simply too high.
You know, back in the days when medieval man was looking out from Europe and thinking about exploring the world was unknown, and map makers populated their maps with dragons. We've got the same thing today. There are people who are afraid to go out into space, and they've populated their maps of the solar system with dragons. You know, we've got cosmic radiation, we've got zero gravity, we've got back contamination. But these are dragons that we can take on.
There are two kinds of radiation astronauts must contend with in outer space: solar flares and cosmic rays. Solar flares are floods of protons that burst from the sun at irregular intervals and would be dangerous to an unshielded human crew.
We are not ready to send humans to Mars right now. We've got to know a lot more about radiation and radiation mitigation. One of the Apollo flights barely missed, like by a week, a major solar event. If it had gone off when the Apollo astronauts were on the way back and forth to the moon, they would have gotten their entire lifetime radiation dose in that one mission. And that's just one solar flare. So that's why we worry about this.
In the Mars Direct plan, Zubrin envisions a central, insulated core where a crew can retreat to while the radiation passes by. The core would be surrounded by all the provisions of the mission. This should stop any harmful dose of radiation from reaching the astronauts.
Basically, you use your pantry as your storm shelter. So a solar flare happens, the alarm bell rings, the crew goes into the storm shelter, they stay in there cramped up pretty tight for a few hours until the all clear rings and they come out. This is going to happen once, it might happen twice in the course of the mission.
The second type of radiation is cosmic rays. This constant rain of charged particles comes from interstellar space and cannot be avoided without many meters of shielding. We can experience some of this type of radiation on Earth at high altitudes. Airline pilots who spend their careers flying high in the atmosphere can receive almost as much of this radiation throughout their life as a Mars astronaut would on a 2.5-year mission.
It's a long trip. It's a 6-month trip there, a 6-month trip back. It's probably a year on the surface. That's a lot of radiation.
The best estimates are that the magnitude of that dose is not that great, perhaps 60 rem of radiation scattered over 2.5 years. Now, 60 rem of radiation delivered over a long period of time like that would not create any noticeable effects at all. It would, though it is believed, increase your statistical risk of getting cancer at some point later in your life by about 1%. Right now, if you're an average American and you do not smoke, you have a 20% chance you're going to die of cancer. This would make it 21. If you're an average American smoker, it's 40. So in fact, if you recruited the Mars crew out of smokers and sent them to Mars without their tobacco, you would be reducing their chance of getting cancer.
With the immense distance from Earth, never before experienced by a human being, with the constant dangers of outer space surrounding their small, life-sustaining craft, and with nowhere else to go, the psychological impact on a crew could be severe.
Fear is real. I mean, it would be, to me, abnormal for a person to not feel the fear of getting on a rocket and launching into space and going to Mars. So I think fear is a very normal thing that all astronauts, in fact, are supposed to have. And I would be afraid to fly with someone who does not have fear.
Some psychologists worry that cabin fever could set in, and the crew might literally go crazy.
The human Mars mission is a more rigorous and difficult condition than most of us experience in daily life. But it is hardly a more difficult situation than many people have endured throughout human history. We could compare the Mars crew to the crew of 19th century or prior sailing vessels, many of whom were away from home for 3 years or more than 3 years, under conditions in which they're eating extremely bad food, without any medical knowledge to support their health, commanded by brutal officers. In every respect, the crew of a human Mars mission with the full support of mission support and the whole world cheering for them and great rewards awaiting for them in life upon their return, is in a vastly superior condition.
The Mars Direct crew will spend most of their time inside the two-story hab, carefully designed to promote psychological well-being despite the confinement.
The space where I think everybody would spend the most time, just like a lot of homes on Earth, would be the galley wardroom area. There would be chairs, a table, some kind of large screen for entertainment. You would have individual staterooms about 4 or 5 feet wide. The ability for them to communicate with loved ones, with colleagues on Earth, I think will be almost unlimited.
A Mars crew will need to be carefully chosen and thoroughly tested to ensure their ability to handle the extreme isolation.
Wow, what a place. What a view, isn't it, John? It's absolutely unreal.
John Young, who went to the moon, used to say that he could cover the Earth by just lifting his thumb up to it. And he says that when you go to Mars, you are going to redefine the concept of loneliness. And so it is very important that the crew be well balanced and well chosen so that they can support each other.
Whoever gets picked to go, they will have to learn to live together for 2.5 years.
If you put out a call for volunteers for the first crew to Mars, they'd be lined up coast to coast. Most people recognize what's left after you go is the good you left behind. And to take part in an adventure of this character, of such a historic character, of extending the reach of the human species, this is something of immortal significance. One of the most bogus threats associated with the Mars mission is the so-called back contamination issue, which is this notion that you go to Mars and discover these virulent disease organisms that you bring back to Earth and destroy all life on Earth.
If we discover life on Mars, one fear is that our Earth biology will have no defense against possible Martian pathogens. Some argue that missions to Mars cannot be risked until we can prove Mars is free from harmful contaminants.
This is completely nonsensical. There's natural transfer of material from Mars to Earth all the time. We get around 500 kilograms of unsterilized Martian rocks landing on Earth every year, and they have been doing so for the past 3-4 billion years. And so if there were Martian organisms that could contaminate the Earth, they've already done so.
Although the prospect of Martian diseases seems remote, lawmakers have required that NASA create elaborate protocol to ensure that any extraterrestrial material stays contained. And like the Apollo astronauts, who spent 17 days in quarantine after their return from a sterile moon, a Mars crew will have to be thoroughly tested for any harmful Martian pathogens.
The probability is infinitesimally tiny. But nevertheless, this is our home planet and it's extremely important and we have to protect it.
The idea of a pathogen on Mars is clearly ridiculous because there is no megafauna or megaflora on Mars for pathogens to infect. So it is impossible to propose a credible life cycle for a Martian pathogen. The diseases that afflict us have been co-evolving with us and our ancestors and near relatives for the past 3 billion years, and they are specifically designed to live inside the habitat of the human body and to overcome its defenses, and they've been engaged in an arms race with the human defenses for those 3 billion years. This is why humans do not get diseases from distantly related species. For example, I don't know of any person who has ever contracted Dutch elm disease, and trees don't get colds.
When the first Mars lander touches down, the crew will be staring out at a new world, a place that in 4 billion years, no eyes have ever seen. The crew won't be alone. millions of television viewers back home will be watching as the first man or woman places their footprint into the rust-colored soil. The crew will savor these moments, for here, someday, a new branch of civilization might begin, and future Martians will remember and celebrate this day. There is much for the crew to do and explore. One of their main mission objectives will be to search for signs of microscopic life. To do this, they will follow the ancient water flows. For on Earth, where there is water, there is life. To help the crew in their search, they will have a pressurized rover that allows them to explore in a comfortable shirt-sleeve environment. This means the crew can examine a vast area around the landing site during their 18-month stay. And there is much to explore. Mars has 58 different kinds of topography and a surface area equivalent to all the continents of Earth combined. If these explorers can uncover the fossilized remnants of indigenous Martian life, they will redefine mankind's understanding of its place in the universe.
For if life arose separately on a planet so close to our own, it strongly suggests that the universe is a biologically rich place and full of life. For some, the ultimate question of Mars, though, is will there be human settlements on the planet? Will Mars become a new branch of human civilization?
As each subsequent Mars mission explores a wider and wider area of the planet over several years, an ideal site for a base will be found, probably one with a thermal vent that can supply water and power. At that point, several HABs will be landed in this one spot, with crews that plan to stay for 4, 8, or even 12 years. The HABs will be interconnected, and a permanent human presence on Mars will be established. This scientific community will have to learn to become self-sufficient, to be able to survive on Mars without supplies constantly being sent from Earth. But unlike any other planet in the solar system besides Earth, Mars has all of the fundamentals needed to make this possible. Its 24-hour and 37-minute day is critical for growing plants. It has all of the elements necessary for creating building materials like plastics, metals, and glass. And it has oceans of water frozen into the soil.
If we can develop this craft of living on Mars, then Mars becomes inhabitable. Not immediately physically, but intellectually. I mean, look, what determines whether an environment is habitable or not? Is Colorado habitable? We're not naturally adapted to live in Colorado. We're tropical animals. No one could survive a single winter night here without technology, such as clothing, efficient use of fire. We invented our way into becoming people that could colonize such hostile environments.
Eventually, with a lot of ingenuity and invention, the scientists will learn to live off the land. They will grow crops in the iron-rich but potassium-poor soil. And they will produce oxygen and energy from the water and atmosphere. Sooner or later, children will be born, the first true Martians. They will grow up to see Mars as their home. With time, more and more people will arrive. These won't only be scientists, but settlers, people who plan to stay. They may come for all kinds of reasons, but to them, Mars will be a chance to start over, to build a new life for themselves.
The well of human social thought is not exhausted by the present age, and I don't think will ever be exhausted. There will always be people with new ideas on how humans should live together.
With Mars so far away, the hold of Earth governments on their colonies will be tenuous. The Martians will need to govern themselves.
Mars is not going to be a utopia. Mars is going to be a lab. It's an open frontier. It's a place where things are going to be tried out. I think we'll see a lot of noble experiments on Mars. Perhaps some of these Martian colonies with their novel ideas based on the best thought the 21st century has to offer, maybe they'll find ways in which humans create society that are more humane and offer more opportunity for human potential.
The ultimate dream of the Martians will be to terraform their planet, to make Mars as hospitable as Earth. This may not be as big a fantasy as it seems.
Here we are on Earth, a world that's very sophisticated and developed and complete. And anything we do is just a subtraction. It's because we live in such a biologically rich planet. When we go to Mars, we have an opportunity that we don't have on Earth. Here's a planet that's died. Here's a world that's not full of biology, probably doesn't have any at all. Well, there, we can actually do something to help.
Once there are large human settlements on Mars that will have significant industrial capability, we could actually start addressing ourselves to the question of transforming the Martian environment itself, terraforming Mars, as it's called, because Mars was once a warm and wet planet, and it could be made so again through human engineering efforts.
With daytime temperatures in the Martian tropical zone averaging around 0 degrees centigrade, and with an atmosphere only 1% as thick as Earth's, exposure to these elements by a human without a spacesuit would be instantly fatal. The first step to terraforming Mars and bringing it back to life will be for the Martian colonists to warm up their planet.
Well, we know how to warm up planets. We're doing it on Earth by putting gases in the atmosphere. On Earth, it's not a good idea to warm up the planet. The temperature is just fine, thank you. We don't need it any warmer here. But in principle, if you could trap the sunlight reaching Mars today, every single photon that's hitting Mars, Mars would warm up in about 10 years. Well, obviously you can't trap every single photon that's hitting Mars, but you can trap about 10% of them with the greenhouse effect. So that would imply that Mars could warm up in about 100 years. Well, 100 years is a long time, but it's not astronomically long.
One idea is to build small, automated factories that produce super greenhouse gases with no ozone-depleting side effects. Although these gases would be unwelcome on Earth, for the Martians they would be an efficient way to trap heat.
Then within a few decades, we would raise Mars by more than 10 degrees centigrade. And if you did that, that would cause massive amounts of carbon dioxide that is currently absorbed into the Martian soil to start to outgas.
Carbon dioxide is also a natural greenhouse gas. As it builds up in the atmosphere, more and more heat will be trapped, which will in turn cause more CO2 to outgas. The process will become automatic, and as the atmosphere thickens, Mars will eventually reach a state of equilibrium and stay warm naturally. The rise in air pressure would mean that the human colonists could discard their pressure suits and walk around the surface of Mars carrying only a supply of oxygen. And as the temperatures rise on Mars, water frozen into the soil will begin to melt out. And for the second time in its history, Mars would have liquid water on its surface. Dry Martian rivers will start to flow. Seas will rise, and there will be rain clouds in the skies. The return of Mars to its warm and wet stage will make it a fertile environment for life. Any indigenous Martian organisms lying dormant will begin to grow. and Mars will be full of Martians. If no native life emerges, or that life is all dead, then humans could begin addressing the idea of bringing life from Earth. At first, it would be simple organisms, perhaps genetically engineered, that would thrive in the Martian environment. Then more complex plants could be introduced. The plants would be right at home in the carbon dioxide atmosphere, and with no competition and a whole planet to cover, they could transform Mars into a green world. Warming Mars so that it sustains life is rapid, but then the slow process of making the atmosphere breathable for humans and animals starts, and that's done by plants. Although the process will happen naturally, if the colonists can't find a quicker way, it will take tens of thousands of years.
This is a philosophical debate. Many people think the universe has a big sign on it that says, "Do not touch. Leave it alone. It was made this way. It is not in our purview as human beings to change anything." I can respect that view, although I disagree with it. I think the universe has a big sign on it that says, "Go forth and spread life." Because when I look around the universe, I think life is the most amazing thing we see. It is just incredible. And we human beings are uniquely positioned to help spread life from this little tiny planet, which it seems to have been started on, beyond. And that's our gift. Earth's gift to the universe, I think, is the gift of life.